So we're going to cover some of the VPC configuration steps in a graphical form, and then ultimately we will do a CLI example later on in this lesson. So again, we've discussed the VPC peer link, right? A little bit more detail about it though. It is a standard .1Q trunk interface. It carries the Cisco Fabric Services message. It carries flooded traffic from the other VPC peer. And it carries STP, BPDUs, HSRP hellos, and IGMP updates. The requirements for this interface would be that the member ports must be at minimum a 10 gig interface, and the VPC peer link should be a point-to-point connection. Now a little bit more detail about the VPC peer keep alive link. Again, it's a heartbeat between the VPC peers. It's used for active-active or split brain scenario when the peer link is down. The packet structure is a UDP message sent on port 3200. It's 96 bytes long. It includes some various information like version, timestamp, local and remote IPs, and a domain ID. The default timers are interval of 1 second and a timeout of 5 seconds. It's important to note that the VPC peer keep alive can be a standard link. It doesn't have to be redundant, and in many cases you might opt to use the management interface on a switch for the VPC peer keep alive. If the VPC peer keep alive link does go down for any reason, it will not create an active failure scenario on the network, but it's very important that you monitor the state of the VPC peer keep alive link and restore it as soon as possible. If the VPC peer keep alive link were to fail, followed by the peer link, it could lead to a disastrous scenario where you would have a split brain scenario occurring on the network. So VPC also implements a configuration check. So both switches in the VPC domain do maintain distinct control planes. So a little bit different than VSS and iOS, where you're maintaining one configuration. With VPC, you actually have an independent configuration on both switches. CFS, again, provides that protocol state synchronization between both peers for MAC address, IGMP, etc. But because these are independent control planes, the system configuration also must be kept in sync. So a little bit about the VPC consistency checks that do occur between the two switches. There are global configuration parameters, and then there are interface configuration parameters. Each one has what's called a type 1 and a type 2. Type 1s are generally more severe than type 2. So globally, if you experience a type 1 consistency check issue, all the VPCs would be put into a suspended state. Type 2 will simply provide an error message. And on the interface, a type 1 will put the VLAN or interface in a state of being shut down. And for a type 2, it will also display an error message. So now let's move on to VPC configuration steps for a VPC member port. Again, the definition of a VPC member port, or a VPC, is an interface that's connected to two of your upstream VPC peers inside of a VPC domain. The configuration needs to match on each peer's interface for this particular VPC interface, and in case of an inconsistency, a VLAN or the entire port channel, again for this scope to this particular link, may be suspended. For example, if you configured VPC 201 on this switch and VPC 201 on this switch, but had a different MTU on both, that would be a type 1 and cause that particular port channel to be suspended. Now, a couple notes on VDCs with the Nexus 7000. So VDCs are virtual instances of a device running on the Nexus 7000, and of course are covered in great detail in another lesson. VPC works seamlessly in any VDC-based environment, and each VDC can have its own VPC domain. So just like you had a pair of switches that can have one VPC domain, each VDC in a Nexus 7000 can have its own VPC domain, again, limited to one VPC domain per Nexus 7000. And then a separate VPC peer link and peer keep alive link infrastructure is needed for each VDC that's deployed. And now let's take a look at the configuration steps before we hop into the actual configuration window. So the following steps are needed to build a VPC domain, and the order does matter. So first, we define our domains. We establish the peer keep alive connectivity. We create our peer link. We reuse port channels and create VPCs, or create new ones for that matter. And we want to make sure, of course, that our configurations are consistent. So now let's hop in to the actual CLI. Okay, so let's start with some of the configuration elements for building a VPC domain. So I have two switches defined here, N7K1 and N7K2. I have a pre-existing management connection between them that we're going to use for our peer keep alive link. So we'll take a look at that real quick by taking a look at our management 0 interface. So you can see here that this management 0 interface is up and defined. And if I pop over to our other Nexus 7K, you can see here that it also has an IP address associated with it. Now, it's important to test connectivity on this management interface prior to configuring vPC. So from Nexus 7K1, I'm simply going to do a ping to Nexus 7K2. And make sure that it's reachable. And it is reachable. I have no problems there, so we can proceed. Now, I also have a port channel interface that's going to be used as our vPC peer link, already defined between these two Nexus 7Ks. This interface is port channel 1. So let's just take a quick look at port channel 1 and make sure that that port channel is up. And it is, and it's up and working. So we don't have to worry about cabling up or getting that port channel up and working. This port channel will ultimately become our vPC peer link. So first and foremost, again, due to the modular nature of NXOS, we need to enable the feature for vPC. So I'm going to do that with feature vPC on N7K1, and I'm going to hop to N7K2 and turn feature vPC on there as well. So the next step after turning on our vPC feature in NXOS is to establish our vPC domain. So I'm going to do that with the command vPC domain, and then I get to set my domain ID. Again, this must be unique across an entire layer 2 domain. So I'm going to set this domain and use domain 10 for this example. As you can see, we've now got some sub-configuration associated with it. I'm going to follow suit and hop over to N7K2 and type vPC domain 10 here too, so we can follow along. And we'll roll back to N7K1. So to establish standard connectivity for our peer keep alive link, which is the next step in the order of operations to establish our vPC domain, I'm going to define the peer keep alive link within vPC. So I'm going to do that with the command peer keep alive, and then I'm going to specify the destination, and this destination IP address is my peer's management 0 interface. And then I'm going to define a source interface as well. Again, this is not mandatory, but it's a best practice, and I would highly recommend doing it. Now, because we're using the management 0 interfaces on this platform, they're bound to the management VRF. So after this, I have to specify the management VRF. If you're not using the management 0 interfaces and are using a front panel interface on the system, it's advisable to create a dedicated VRF for the vPC peer keep alive messages. So I'm going to issue that command on N7K1. And then I'm going to hop over to N7K2 and issue a similar command, but I'm going to reverse the IP. So my destination on N7K2 will be the management 0 address on N7K1. Now, the next step in establishing our vPC domain is to define the peer link itself. As we discussed earlier, we're going to use interface port channel 1 for our vPC peer link. So I'm now going to move back to N7K1 and access that port channel by going into interface port channel 1 and defining this interface as our vPC peer link with this command. So you can see I'm now exited out of VPC configuration mode and into the interface configuration mode itself. I'm going to specify this as our VPC peer link. Now, it's important to note that by specifying this as the VPC peer link, the spanning tree port type will be changed to port type network. This will enable bridge assurance on this link, and again, is really the only place in a VPC environment where bridge assurance should be enabled. I'm now going to make the same configuration on N7K2 for port channel 1. And it's going to give me the same message. So those are some of the basic steps to establish the VPC domain between the two Nexus 7Ks. Now, operationally, to gather some data about the state of VPC, I'm going to issue the command show VPC. This is going to give me some useful information about what's happening between the two systems that I have here. So you can see here that my VPC domain is 10. My peer status has been formed okay. This means that everything is looking good on the VPC peer link. The peer keep alive link status is alive. Now you'll notice here that I have a configuration issue between these two switches. And I did that on purpose so we can illustrate what would happen in this scenario. So again, a type 1 global consistency issue needs to be resolved, and we'll troubleshoot that here in a second. So by default, I also didn't manipulate the VPC role. I could have, inside of the VPC domain, set a role priority to make N7K1 the primary VPC switch. As you can see here, my VPC role is secondary. I talked earlier about operational status. As you don't see any secondary comma operational primary, you know that there hasn't been a failure or the VPC role hasn't flipped from one switch to another. So now we have a VPC type 1 configuration issue and we want to troubleshoot that. So VPC makes it very easy, instead of having to manually parse through configurations, to figure out where that type 1 configuration issue exists. So I'm going to issue the command show VPC consistency parameters. And you'll see here that there's a number of areas in which I can look at the consistency parameters between the two switches. I can look at the global parameters, which I will because that's where our type 1 exists now, or I can look on a per interface basis to make sure our interfaces are in sync. I'm going to look at the global ones, and I'm going to execute that. So I'm running this command from N7K1. So this is going to give me all of the global values that must match between the two Nexus 7Ks in this example. And you can see here that we have a difference when it comes to our spanning tree configuration. So on N7K1, the STP mode is MST. On N7K2, I'm running rapid PVST. So you can see there that now that is a type 1 VPC consistency issue, and will cause VPC to be suspended until I resolve that. So I'm going to go ahead and resolve that real quick by spanning tree mode rapid PVST. And then I'm going to issue the command show VPC again. Right? Now you can see that our configuration consistency status has been successful. And if I issue the same consistency parameters configuration again, you can see that I have both of my modes in rapid PVST mode. So now let's look at how to configure an actual VPC or a VPC to something that's attached to both N7K1 and N7K2. So on interface Ethernet 121, I have a host attached. So I'm going to create a new port channel, and I'm going to call this port channel interface port channel 100 for this particular host. This port channel is going to be a switch port because it's a host, and it's going to be an access port. So that was a simple configuration for interface port channel 100. I'm going to repeat that configuration on N7K2. So now we've got both of those in sync there. Now the next step is inside of my Ethernet 121 interface, I'm going to bind this to port channel 100. So I'm going to do so by saying channel group 100 mode active. I want to leverage LACP here. Now you'll notice that it gave us an error. So one of the other tools that you can use within NXOS to bind ports to a port channel in the event that the command failed is to force it. Now this command failed because I had some other configuration already on interface Ethernet 121. It's actually accessing a different VLAN. So what I can do to bind interface Ethernet 121, instead of saying channel group 100 mode active, I can say channel group 100 force mode active. And basically what this does is forcibly replaces all the configuration on interface Ethernet 121 to make it match my port channel. I'm going to do the same thing on N7K2. You can see it failed again. So I'm going to do the same thing and force it. So my port channel is not in the state of being up now. So I've now configured both the port channel and bound my host interface to that particular port channel. So the last step in order to finish our vPC configuration for this port channel is to give a vPC ID to the port channel to make it a vPC. Otherwise, it's just a standard port channel on the system. So I'm going to go back into port channel 100, and I'm going to say vPC, and you'll notice now that I have the ability to specify a virtual port channel number. So this is the vPC ID for this specific port, outside of the domain and all the other elements that are associated with it. So you can assign any virtual port channel number in this range to this interface. As a best practice, I like my vPC IDs to match my port channels. When I'm troubleshooting, it helps to make sure that those line up. It's not required though. So I'm going to say that this is vPC 100, and I'm going to hop over to Nexus 7K2 and repeat the same process. I'm going to hop back to N7K1 and issue the command show vPC again. You can see now that my port channel 100 is not up yet. I haven't powered the host up. I wanted to prep the configuration first. But you can see that our vPC status for ID 100 and port channel 100 from a consistency status is correct, and everything is all right with the configuration. It's just down because my host is currently down.